Hello and welcome to another video of Corpnce. Myself Ronu Savio. Today we are going to see some of the issues that beginners face while they are learning bitwise operators. So when I give negation of 5, I am getting -6. Wait, is something wrong with Python? So in bitwise operators you have seen and, or, left shift, right shift, and negation is one of the bitwise operators too in Python, and it is known as the negation not operator for bitwise. So in order to understand these bitwise operators, especially these negation operators, you have to understand how the information in your computers are stored. Let's make this easy for you guys with an example. In this lamp, I have the switch, and this switch I can have two information, like I can make the lamp on and off. So if I pull it, it's off now, and if I pull it again, it's on. So here the switch can hold two information, on and off. Let's say on holds the information as 1 and off stands for the information as 0. So you saw that a switch can hold two information, 0 and 1. What if I wanted to store more information, 3 or more information? Then don't you think I have to add more switches? So if you have a combination of on and off, you can have like literally zeros and ones. You are having more combinations of information. This is the same way how your system also stores the information. Whatever you feed in your system is nothing but stored as zeros and ones, combination of on and off. So the more switches you have, the more information that you can store in your system. The information stored in computer memory are of two types, RAM and ROM. So RAM is your random access memory where it stores the information temporarily while the system is on, and it's very fast and efficient. Whereas ROM is your permanent memory, and we'll talk about that later. Right now we are focusing on how RAM will store the information. The switches inside the computers are made of transistors. These transistors control the flow of electricity. On means the current flows and off means it doesn't. These transistors are very tiny. Billions of these transistors can fit in the tip of your finger. So all these transistors are arranged together to form the computer chip, the brain of your device. Bit is nothing but the smallest unit of data. 1 bit represents 1 switch, and 8-bit represents 1 byte. Why do we need 8 bits to represent 1 byte? Because we can represent 256 different combinations, enough to store letters, numbers, or even colors of an image using 8-bit. Also notice that computer stores memory in the powers of 2, not in any other random numbers. That is why you often notice that any memory card or pen drive will be in the size of 2 GB, 4 GB, 8 GB, all in the powers of 2. Now I will show you how to represent numbers in binary representation. So here we'll start with 2 power 0, because initially a switch by default should be of any one number. So we'll on or off. Then we have 2 to the power 1, 2 to the power 2, and 2 to the power 3. Okay. So I am using 4 switches here, 4 combinations of switches. So it is 4-bit representation. All these powers I have written here are nothing but switches. So 2 to the power of 0 is nothing but 1, then we have 2, then we have 4 and 8, right? So I can erase this one. This is nothing but 4-bit representation. And here, let's say initially I have to represent 0. So I can say all the switches should be off in order to represent 0. 0, 0, 0, 0. So all the switches are off. So this is nothing but representing 0. Now let's say I have to represent 1. When I have to represent 1, you can see out of these 4 switches, the first switch, nothing but the first bit is nothing but 1. So keep that one on. So when I give 1, it's nothing but it is on. Rest all the switches are 0. So this represents 1. Now I need to represent 2. So I know that the second switch should be on and rest all should be 0. So then I can represent 2. Now you see, when I need to get to the third number, number 3, I have to have a combination of first and second switch. The reason is 2 plus 1 is 3. So I need to represent 3. So I have to keep this switch on and this switch on, the first and the second switch. Because the first switch has one combination and second switch has two combinations. So 2 plus 1 is 3. Hence we get 3 and we can keep rest of the switches 0. Then we have 4. In order to reach 4, I cannot reach it with first two switches being on. I have to jump to the next switch. So next switch should be 1 and rest all should be 0, because you know the next switch is nothing but 4. So we get here 4. Then let's say I need to reach 5. So I can say, okay fine, I can get a combination of, I need 4 plus 1, the first switch, and then I reach 5. This is how you represent numbers in binary. Now that you see that you can represent numbers in binary like this, we will see how the negation operator in Bitwise works. So here when I say negation, it's nothing but it's negating the value. When you give true, it's going to give false. When you're giving positive value, it's going to give negative value. So in Bitwise, we give negation of a particular number n, it's going to give you negative value with plus 1 to it. So what do I mean by this is that when I say negative of 5, let's say for example, it's going to give you minus 6. Negation of 7, it's going to give you minus 8. So why is that happening? The reason is, the things, in order to understand these parts, you have to know what is 1's complement and 2's complement. So what happens in this 1's complement is that you have these positive numbers. So initially what I've shown you, those 4-bit representation was positive numbers. So in 1's complement, you give the negative numbers here. So here you can see I have negative 0, negative 1, negative 2, negative 3, negative 4, negative 5. And in order to represent negative 0, I have to convert all the bits of 0 to 1, 1, 1, 1. And then for minus 1, I have to do 1, 1, 1, 0. And then I have minus 2, so I have to reverse the bit for positive 2, that is nothing but 1, 1, 0, 1. And then for minus 3, I have to do 1, 1, 0, 0. And for minus 4, it is 1, 0, 1, 1. And minus 5, it is 1, 0, 1, 0. So here I have just shifted the bits in order to represent negative bits. And now in 1's complement there is a problem where we have negative 0. So negative 0 is not actually existing in reality. And let's do some calculations. Let's take plus 3. So you know already how to perform addition in binary. If not, I'll just show you. So I'm going to take plus 3 and minus 3 and perform some calculations. So plus 3 is nothing but 0, 0, 1, 1. And minus 3 is 1, 1, 0, 0, the opposite of it. Now before we start the calculations, I'll just show you how actually binary calculations work. So here when you have 1, 1, it is nothing but 0 with 1 carry. And then you have 0, 1, it is 1, and 1, 0 is 1. And 0, 0 is 0. So here we'll apply the same calculation logic and we'll see that 0, 1 is actually 1, and 0, 1 again it's 1, 1, 0 is 1, 1, 0 again 1. Now you can see we are reaching the value as negative 0, which is very close to 0. You can see the problem here, we are not reaching the actual value. So now to tackle this problem, we are going to use 2's complement. So you saw in 1's complement we had the problem of negative 0. Every time you try to make calculations, you are reaching almost the value but with 1 bit difference. Like let's say you took negative 3 and positive 3, you are reaching negative 0 here, which is almost close to positive 0. So what do you do in 2's complement is that we remove this negative 0 by shifting 1 bit. So here you can see in 1's complement you have negative 0 as 1, 1, 1, 1. What you do in 2's complement is that you shift the bits, so you remove this negative 0 and in the position of this negative 0 you have negative 1. And same way in 1's complement you have negative 1 here, the same position is taken as negative 2 in 2's complement. You see, every number, negative number, is shifted one bit. So in minus 2 position we have minus 3, in minus 3 position we have minus 4, and in minus 4 position we have minus 5, and in minus 5 position we have minus 6. This is how 2's complement work. Now let's try the same calculation and see if we are reaching negative 0 or positive 0. So let's try. So plus 3 is nothing but, if you look at here, you can see our plus 3 is 0011. And minus 3 is nothing but, in 2's complement we have it as 1101. So let's try it, 1101. And now if you do the calculations, you see 1 1 it's nothing but 0, 1 carry, 1 1 again, 0 with 1 carry, 0 with 1 carry, 0 with 1 which is neglected because we are representing it in 4-bit. So when you do this, you are getting positive 0. So this is how 2's complement help you tackle the situation that we are facing in 1's complement. So this 2's complement is the reason why when you are using negation of any value in bitwise, you are getting the next value of it. So when you are saying negation of 5, you are getting minus 6. This is the reason because of 2's complement. Now that you understand 2's complement, let's see the other operators in bitwise. So the next operator we are going to see is the AND operator. AND operator is represented with this symbol and here let's take two switches, 0 0. I'm keeping both the switches off, so in AND operator this will result in 0. 1 0 will also result in 0, 0 1 will also result in 0, 1 1 will give 1. AND operator only works if both the switches are on. Okay, let's perform this with two numbers. So here let's say we'll take number 3, so that is 0011, and number 5 0101. And here when I perform the AND operation on this one, you can see the first one will be 1, 10 is nothing but 0, 01 is nothing but 0, 00 is nothing but 0, and here we are gonna get 1 as the answer. Okay, now we looked at AND operator. Next we will see on OR operator in bitwise. So OR operator is represented with this vertical bar, and here let's take the two numbers. So before we take the two numbers, let's try these two switches. So 0 0 is nothing but 0, 0 1 is nothing but 1. So either of the switches should be on for OR operator to give 1. So 1 0 is also 1, and 1 1 is nothing but 1. So let's perform OR operation on 3 and 5. So let's say 0 0 1 1 and 0 1 0 1. So here when I perform OR operation, you can see I am getting 7 as the answer. You can check it out, this is 7. Okay, now let's perform XOR operation. So what is this XOR operator? This is represented with a cap. And XOR operator, let's take two switches, 0 0, it's nothing but 0, 0 1, just like OR operator, it's gonna give you 1, 1 0 is also gonna give you 1, but when you have both the switches on, it's gonna give you 0. So this XOR operator works when both the switches are maximum or minimum. So either of the switch should be on, but not all the switches should be off or on, right? That is XOR operator. So let's perform XOR operation on 3 and 5. So 0 0 1 1 and 0 1 0 1. Okay, so when you are performing XOR operation on this one, so initially the first one will be 0, this will be 1, this will be 1, this will be 0. So this is nothing but 6. You are getting the value 6. So this is XOR operator. Next what we have is left shift and right shift in bitwise. So left shift, we represent it with this symbol. Okay, and let's say left shift of 5. So I want a left shift 5 with 2. Okay, 2 bits, shift 5 2 bits left. Okay, that's what I'm saying. So initially, you know, phi is nothing but 0 1 0 1, right? And when I shift phi 2 bits to the left, 2 zeros should be added to the right. So it's nothing but 1 0 1 0 0, right? So this is nothing but shifting phi 2 bits to the left. So this value turned to 20. So here you can see when you're left shifting, you are increasing the value. You can say you're gaining more information or something like that. When I say right shift, it is represented with this symbol. Okay, so greater than symbol. And here I'll say right shift the value 2 bits. Now what happens? Same thing where phi is 0 1 0 1. When I right shift, the phi, the bit representation of phi is shifted right side for 2 bits. So here we are losing the information. The first two value will be gone, so it's going to be 0 0 0 1, because these two values, the first two bits have been shifted. So when you are going to the right side, the left values have come to the right, so you are losing two values. So now this is nothing but 1. So you can see in right shift you are losing information, but in left shift you are gaining information. That's all for this video. I hope this video helped you understand the tricky concepts behind bitwise operators. If this helped you, do subscribe and hit the bell icon for more updates. Thank you.